to Lunch and Learn. Today is November 15th, 2022, and this is the League of Women Voters of Salina Lunch and Learn. In the League of Women Voters, well, we are a nonpartisan, not-for-profit organization that works to increase participation in the governmental process, the political process. We don't support any particular candidate, but we do take positions and study them and lobby for them in certain cases. Our board has been curious for a long time about all of the recent earthquakes in Kansas. It's not a political issue very much right now, but it is a question that we've had. And so we are really happy today to have a professor from K-State, Dr. Abdelmoneam Raef. He says he goes by Raef, so if you want to talk to him, you can call him Raef. He is a professor of geophysics at K-State, and I'm going to read you a little bit about what his bio online says. He teaches K-State courses in geophysics, seismic data processing, and seismic analysis. His research interests are in 3D and 4D seismic studies of CO2 injection for enhanced oil recovery and carbon sequestration, non-invasive location of fractures in highway foundations, and the use of geophysical tools in forensic geology. He works closely with other Kansas agencies, including the Kansas Geological Survey and the Kansas Department of Transportation. Please welcome Raef. Thank you.
Well, I'm really pleased to have the opportunity to be talking to you about earthquakes and seismicity in Kansas. Very comfy gathering because this moment I don't have to use a microphone as I do in the classroom. So it's going to be easy for me today. I will try to present you with an account on earthquakes in general and how we in Kansas fit in the bigger picture. And by the bigger picture, I mean globally, where we are in terms of seismic risk. And also we're going to try to understand why we have had such surge in seismicity over the last 15 years or so. Okay. Here the title Earthquakes and Assessing Fault Reactivation Potential. It doesn't show there for some reason. Okay. Well, it's a new discovery. All right. But I can do with the course of
Okay.
no, it does change. It does change. That doesn't point.
Oh, I see.
Yeah. But the fact is not only South Central Kansas. If nobody from Oklahoma, today I'm going to blame Oklahoma for them. Okay. We'll see today why should we blame Oklahoma. So let's get started. If you look all these yellow dots around the globe, all the yellow dots we have here actually the epicenters of earthquakes globally. And you can see they're not distributed randomly. There is some sort of order. That sort of order actually pointed scientists to, or actually validated the plate tectonics theory. It is data that is telling us that the globe, seismicity is not distributed uniformly worldwide. But there are areas that are quite no epicenters. You can see seismic Illinois or the Midwest away from what is very well established as belts of seismicity globally. Okay? And in fact, using the epicenters of earthquakes and also the locations of volcanoes, these these two data sets pointed to the outlines of tectonic plates. By this, we could define the different tectonic plates. Right? As you can see, the entire North America and actually part of the northern Atlantic Ocean were a North American plate, tectonic plate. The Midwest, the entire Midwest, and also the East, away from tectonic plate boundaries. Okay. So in terms of the global picture of earthquakes, in fact, we should have very low risk, as we'll see in the next slides. So these are the different tectonic plates outlined, and based on kind of the type of boundary, they are coded by the type of boundary. And you can see the west, where it's close to plate boundary. That's why we're not surprised to see high seismicity in California, for example, okay? Because it is there where we have the San Andreas fault, okay? And it's very well established active seismic area. So what is going on? Why do we have noticeable seismicity? We'll see, these are the tectonic plates, but inside the plates, or the interior parts of the plates, go ahead.
Sorry to interrupt, but convergent and divergent and transform
Yes.
types, does that mean that California is pulling apart
California,
or going together?
The Pacific plate moving sideways relative to the North American plate. Okay. The San Andreas fault is kind of that type of boundary transform. The green line there.
Oh, yeah, okay.
This
That's where that.
boundary.
Mm-hmm. Huh.
There's three different types of boundaries. We don't go over them today, but just
Yeah.
all right. When we have a major earthquake, well, it is something that would be felt globally. Okay? And example of this, the Sumatran earthquake in 2004, is close to Indonesia. It has ruptured about actually 700 miles length of the ground of the ocean floor. So you can imagine the amount of energy associated with such large event. It was 9.1 Richter scale. It has caused a tsunami that was felt actually in all this area. And it travels at high speed, that is, well, across the ocean in about 11 hours. The numbers you see in the ellipses, the number of missing and dead, actually because of the tsunami hit coastal areas that are heavily populated. Okay? Fortunately, even if we will have earthquakes, major ones, where we don't have oceans close by here in Kansas. So we're safe in this regard. But those major earthquakes, actually, they do many great jobs for us. They are kind of our imaging tool. They travel through the entire globe. That is how we came to know about the Earth's interior and what are the materials there. Nobody could drill and reach out and extract samples from the deep interiors. So earthquakes provided us information about the Earth's interior. And this is how we know when there is solid core, there is mantle, there is liquid outer core, there is mantle, there is lithosphere. In fact, through data from earthquake seismology. Another bounty from earthquake seismology by the theory and principles and data that may come from earthquake seismology, we can monitor explosions. worldwide. So no one country can conceal a nuclear device testing, for example, globally. There is a network listening 24/7 to monitor the nuclear test and treating. So earthquakes, they are not all evil. They do provide us some information.
I neglected to mention that you are from Egypt, and I wonder if your home is on this map.
No, it's there, far away.
Okay, right there. Thank you.
The destruction from the Indonesian earthquake in 2004 was really on a massive scale. The Banda Aceh is a heavily populated city. Literally, it was wiped out. That's before and after. So when it comes to seismic risk, we do need to understand the risk, estimate it, develop policies and measures to really save lives. Well, the city was basically Banda Aceh, Indonesia, and was reduced to rubble, in fact, just as you can see. So let's familiarize ourselves a little bit with the terminology we use. I just mentioned epicenter. What's an epicenter? If a fault, or basically a major fracture and the subsurface would rupture, when the focus of the rupture, we call it focal point or hypocenter, the projection hypocenter on the surface, the vertical projection, that's the epicenter. And they don't have to be vertically, just because the fault here is vertical. There can be any fault can produce an earthquake. We do record once a rupture will take place, basically a fault would be activated. Then the energy would spread in the form of mechanical energy. Okay? That can be recorded at surface stations like station 1, station 2. Station 1 will record first because closer to the epicenter. The kind of waves we'll see is not one type of seismic waves. We have 4 different varieties of seismic waves. Not all of them cause destruction. Actually, it is only one type that is responsible for destruction in case of a strong event. So any type of faulting is capable of producing an earthquake. When do we activate the fault? Okay? If slippage will take place, well, they will be manifested in the form of an earthquake. So these are different types of faulting. Well, any of them is capable of producing earthquakes. So what are the different energies that we may encounter or measure? Okay. The focus of an earthquake can be at depths of actually 5, 6, 3 miles, more even. It can be above 100 miles in depth. It depends on where. Okay. In some places, we will not see deep earthquakes. Other places, shallow. But all earthquakes will produce surface waves and body waves. Surface waves will propagate close to the surface. Okay? Actually, those ones that cause most of the destruction, if not all, because they do shape buildings vertically and also laterally. Okay? Engineering people say, well, structures are more capable to withstand vertical stresses, but no horizontal shaking. Horizontal shaking buildings are not designed to actually sustain horizontal shaking. As you can see there, you see surface waves does shake the ground horizontally, okay? And also vertically. there are two varieties of surface waves, one called Rayleigh surface waves, and the other one is called love waves. It has nothing to do with love. It is, it is destructive, right? Because of the ground motion associated with the wave propagation. The body waves actually travel through the entire planet, okay? So on the subsurface. And also very useful to bring actually information about the interiors of Earth and what we encounter, different properties or different velocities, the actually proxies of different composition of different structures. Okay, let me play this animation to actually imagine the difference between P waves. This is kind of body wave. And it is faster, it does arrive first. So this computer doesn't like me to move forward.
Yes, very cool.
I'm going to skip this. So basically, you can see the ground motion there is, you can say, back and forth, and in the same direction of the travel. Okay. Ground motion here is actually perpendicular in the case of shear waves. Okay. The stress involved with shear wave is shearing stress. There actually the deformation is compressional. Okay? So people may think of the waves, what they cause as they propagate through the medium, what kind of deformation. Okay? The deformation caused by the wave propagation in such case is elastic deformation. Ground come back to you for the passage. Okay? That's why when the energy is not consumed quickly, it can travel through the entire planet. It's elastic. If it's just lost in inelastic deformation, well, it's lost. There's no travel. If you want to design your own instrument to measure earthquakes, well, it's not difficult. The principle itself is really simple. Here you can see this is a frame that is fixed to the ground. And when the frame will shake with the ground, so this is fixed to the ground. A mass is suspended, so the mass there will be inertia. Basically, the mass will not move with the frame at the same time. And it's like if I move my hand this way, maybe if you look down there, the movement is amplified. Okay, that simple principle actually is there. If you attach a pen there, it's going to capture the movement, the ground motion, okay, into a record, analog record. Of course, modern ones record. Here you can say, well, this is just one type of ground motion. Yes, that's correct. But modern equipment can capture actually three components: north, south, east, west, and vertical component. A seismogram, well, looks like that. P waves, S waves, and surface waves. You see the amount of energy in surface waves is a lot, okay, compared to the energy in the shear waves and the P waves. That's why those guys cause most of the destruction, surface waves. Let's look to an example here on how do we actually determine the epicenter or locate the epicenter of an earthquake? Well, all what we need at least 3 stations. The 3 stations are going to give us 3 seismograms. Okay? The 3, like you see here in Colorado, these 3 stations, well, they're not going to be at the same distance from the epicenter. Okay? And that would be translated, you see, I said they are not going to be at the same distance from the epicenter because the distance between P and S waves is different. It is 73 seconds, 57 seconds, and 14 seconds. So the 3rd station is the closest to the epicenter. Okay? It's like if you're traveling in 2 cars, and as you travel, one car is faster than the other. As you travel longer distance, the separation is going to increase, the difference between the 2 vehicles. This is similar. So we use such PS interval on this axis, and in fact we use kind of standard curve and get, for the 3 stations, we'll get distance to the epicenter. And we get 3 distances, then it becomes actually a triangulation problem. Then we can locate with the location of the epicenter like that. Of course, this is all done on a computer in a few seconds and based on many stations, not only 3. Because the more stations you have, you get better accuracy. Okay? In terms of magnitude, we use the maximum S wave amplitude, the shear wave amplitude, just right after the P waves. That is the bracket for shear waves. And for the 3 stations, and you see that is an homogram. We have from this axis amplitude, the other axis is the distance. We put the distance from the previous line, distance in the center. Connecting the amplitude to the corresponding distance, when you get 3 lines for the 3 stations, that's pointing to 4.1 magnitude at vector scale. Of course, that can be done not in a manual way, but just to give you some idea about how it is measured, the size. If you check out seismic hazard map for the US, you see we're in Kansas, we are in the green, right? Low risk of seismic, of seismicity in general. Unlike with the western parts of the country. Okay? Well, now we know why, because this is close to tectonic, to the boundary, the tectonic plate boundary. With the exception here, this is the New Madrid seismic zone. All right, so let's see in new seismicity for Kansas and Oklahoma. What is the story? Well, we see there, these are on this axis will be cumulative number of 2.5 plus earthquakes in magnitude. And look how the curve is just hugging the horizontal axis. And look, it's taking off starting from 2010. It has been doubled more than 15 times. Okay? So that's a very significant phenomenon. Okay? So what is the story? Scientists actually try to understand what's going on, what has changed. Okay? that is because the background there, that is the natural level of seismicity in the area. But when comparing what they have seen, this observation, with enhanced oil recovery, saltwater disposal, I mean, injecting fluids in the subsurface, well, that has been increasing, okay, for all three different types of fluid injections. Well, the increase is correlating there with the increase in the number of earthquakes in the area. And that was for Oklahoma, this days, right? And in fact, during a talk that I attended personally, they reported, the Oklahoma Geological Survey, they reported that around 2015, they were injecting about 500,000 gallons every day in the subsurface. Just imagine you are injecting large volumes of fluids under your house. At some point of time, you want to destabilize it, right? Because you weaken the strength of the subsurface. And in such case, well, obviously, we do weaken the strength of faults. The frictional strength, if we weaken it, well, it won't slip. Right? That's an earthquake. And this is when data from, actually, you see from 2014, the number has really peaked, okay? It has, so what happened? It has started to decrease again, from this 2018. In general, if you fake a trend, well, it has decreased. Well, it has decreased because in 2015, the Kansas Corporation Commission, the Kansas Corporation Commission, the KDHE, and Kansas Geological Survey, they actually produced or issued regulations for the volumes injected and the rates, not only the volume, because rates matter. Okay? And well, a decrease has been noticed since actually enforcing those regulations.
So they couldn't, the Kansas legislature can't affect Oklahoma though, right?
No,
This is
it has
just
to
in
do
Kansas.
with their business. That was here, this data for Kansas. Yeah.
So I guess my question would be, does some of the injections in Oklahoma, do they affect Kansas? Or is this actually
They do.
mostly because of Kansas?
If they are producing earthquakes 5+, we'll feel them here. Okay? Even though the epicenter in Oklahoma, we will feel it here. So the KCC regulations actually was introduced in 2015. Once they noticed that crazy surge in seismicity. Prior to 1977, when these are the events, the green dots, these are epicenters of earthquakes. Okay. Compare with the next, let's say where so many dots more, and actually all over Nebraska, also Kansas. But we'll see that a lot will actually be, because that is between 1977 and August 1989, okay, this data. Well, the background seismicity of earthquakes can be interpreted actually due to having major structural elements in Kansas just naturally, that is tectonics, is not related to any human activity, okay, or man-made intervention. These are Nemaha Ridge, that's a tectonic element. Also the mid-continent drift, there are faults naturally there. And they do produce, these are trends that are capable of producing seismicity, but that is kind of the background seismicity, not anything on the order of magnitude as we have seen in 2015. Look at this is between 2015 and 2016, over 6 months only. Well, that's the number of actually recorded earthquakes and cancers. And all of them, well, there is a concentration, as you can see, in Sumner County and Harper. Okay? So it's not really correlating to the structural elements that we have seen a little earlier. Right? So what's going on there? Well, injecting fluids, right? Wastewater disposal fluids, and also actually enhanced oil recovery fluids, hydraulic fracturing, etc. And the idea is that why fluids would cause earthquakes? An earthquake is coming from deep, actually from about 5 kilometers depth, and we're injecting shallower than that. Well, fluids find its way down to the faults in the basement, the hard rocks. And actually, there are numerical or mathematical relationships that relate poor fluid pressure to the reactivation potential of faults. We'll see a glimpse of that in a little bit. Okay? It is like if the fault is strong, okay? No intervention, no fluids going into the fault plane. So it's kind of locked. Okay? If you both inject the fluid and fluids are arriving there, well, they push the two sides of the fault apart. So they unlock, they make it easier to slip. Okay? This is just to do it in a simple way, away from mathematical equations, but the thing has its own roots. Mathematically can be described correctly. That's each month actually from 2013 to 2018. 2015, the peak of 2015 was really scary, and there were the KCC issued regulations. We have seen decline in the seismicity, and hopefully it will at some point of time reach the background. Okay, that would be good. It is just the getting things to neutral, that The depth is average about 5.6 kilometers, okay? And when divided by 1.6, you get the miles, right? So what is the story? It is at depth, but we're injecting there, okay? Well, fluids under pressure finds its way through when vertical faults, open faults, and also when it may cause on these faults, the pore pressure will increase, will unlock the fault, make it slipping. Okay? That's how I feel. And well, these are the number of events at each depth. Okay? A few of them and within the Arbuckle, this is where most of the Arbuckle formation, that's subsurface formation, rock formation, where a lot of wastewater disposal is really being done there. If you see here, that is well, a little bit a standard graph that you can really sketch different stresses, principal stresses, sigma 1, This is sigma 1 minus P sub F, that's basically subtracting the pore fluid, okay? And this is sigma 3, and this is sigma 3 minus pore fluid. So what happens if you increase P sub F, the pore fluid, injecting more fluids? Actually, this circle will hit this line. This line is basically, it does represent the frictional strength of the fault. Okay? So once you are exceeding the frictional strength of the fault, well, an earthquake will get triggered. Okay? Because these guys, the sigma 1, sigma 3, well, they're just the state of stress, the natural stress is you intervene and tip the balance by putting fluids, okay? Then you move from the stable zone to the unstable zone, okay? Then where actually slippage will take place and an earthquake will just start. All right. Most of the new seismicity happened in these two counties, Harper and Sumner counties. Okay? Because there is really high volume of injection activities in these two counties. Okay? The USGS installed seismic stations, additional seismic stations in the area, but also actually KGS, the Kansas Geological Survey, installed the stations, these in green triangles, to kind of monitor and get better recording for earthquakes in the area. These are the recording, and you see with Harper, Sumner County, with the lion's share of induced seismicity. Some of the trends, well, there are faults there. This is the same map with overlaying faults, the solid lines there. Okay. So it is simple. Dump a lot of fluids, will find their way to the fault planes. They will, because it can be a delicate balance. It doesn't need too much of pore pressure to actually tip the balance. If it is critically balanced system in terms of stresses, well, it can trigger an earthquake with change in pore pressure. Okay? And there is one factor that actually not mentioned often, but in my view, it does have an effect. Water itself has lubricating nature. Okay? We do experience this. If a little bit of dirt and rain, well, likely you will slip on it. So it's not only the pore pressure, the fluid pressure, but also the lubricating nature of water is playing there. Go ahead.
Does it at some point, at some depth, the fluid vaporize? Does it vaporize? I mean, how far can the fluid go down before the heat of the substructure might vaporize the fluid?
Yeah, that's a good question. Actually, it does vary from one location to another based on what's called the geothermal gradient. In some areas where, and even with depth, as becomes vapor, but not at 5 or 6 or 7 kilometers. We will need, well, not actually less than 15 kilometers of depth. Okay? Because there, 15 kilometers of depth, that's kind of established cutoff. Beyond that, you go into what's called ductile deformation, where the heat is enough for thing, if you apply stress, you will bend the material, not fracture it. Okay? And therefore, faulting is not encouraged by the prevailing system. Okay? Below 15 kilometers depth. Okay? Deformation happens in a flow mode, not in fracture mode.
Huh.
So structural geologists call it brittle deformation above the 15 kilometers of depth. Below that, we call it ductile deformation.
Professor, did these map fault lines actually predict where oil would be found if there was fracturing? Or they just discovered that serendipitously, when they fracture, they happen to be close to these fault lines that you have demonstrated?
Faults do play a role in where to drill, okay, based on the structures, and you are targeting which formation, which rock formation. But you're right, these faults also may, if they are in the sedimentary cover, they may play a role in guiding hydrocarbon migration, okay, movement of hydrocarbons from the source to the storage, to the reservoir. So people who are doing exploration seismology look into things like that, migration pathways for hydrocarbons. But if it is in a basement, below the sedimentary cover, well, you will have no relationship to hydrocarbon migration. All right, so if we have faults, are they all equal? Are they all have the same likelihood of being reactivated? No. It depends on their orientation. Okay? Some orientation is favorable, other orientation may not be favorable at all. And there, in fact, when you faults close to east-west, they are not favorable for reactivation. Okay? It's not easy to reactivate those faults due to their orientation and the prevailing state of stress. Okay? So not every fault is easy to reactivate. Okay? Depends on its orientation. There are two sets regarding fault orientation, the north 60 and north 110. This 110 and north 60 trend. Okay. The north 60 trend is more favorable when it comes to reactivation, okay, than the other trend, which is the north 110. These are the two sets, prevailing sets. I will just mention this briefly here. The activation potential, it is a value that you can calculate. Okay? And you can see there is going into there the shearing, this parameter actually with the shearing has to do with the shearing strength of the fault. And this is where it has to do with the normal stress, the stress perpendicular on the fault plane. Okay. Without going into much of details, but these are where they can be resolved for any state of stress. You can resolve and know how much is in a shearing direction and how much is perpendicular to the fault plane. And that can go into actually calculating Q. And you see, where pore fluid can be also calculated, and Q is there appearing in this relationship. There are several scientists who actually developed methods of really coming out with a parameter that will tell us the fault reactivation potential. With some, we call it slipping index. right, slipping potential. So what do? You plot your fault, any fault, plot it. This is representing the state of stress, and warmer colors. This is where we faults that we plot there based on their data, their orientation, and their depth, and their structural information. Faults that will plot there, and the red, well, these are favorable for reactivation. Okay? So actually, you can map your area and define existing faults, which ones you should stay away from or not inject in the vicinity of such faults. And those who are plotting, say, in the blue, okay? Like with this event, they're plotting in the blue. So these are based on actually the Q value of the fault reactivation potential. We have, well, actually in the area, in Sumner and Harbor, we have over 70% of faults have been assessed favorably for reactivation. Okay. And about nine fault planes, 9 only unfavorable, plus 19 misoriented faults. These are really very hard to get activated, so they are also safe. These together will make 28 faults. In fact, they are unlikely to get reactivated. And you can see on the frequency, this is the Q value. What is coded red is actually the one that are most likely to get reactivated, the faults. All right, this is an interesting sketch here, kind of giving the favorable orientation is in this way. You see parallel to the Maharaj. So this orientation is kind of, you may say, this set of faults, this orientation, is in fact somehow critically balanced. It's not difficult to get reactivation of the fault. Tip the balance in terms of pore pressure. Higher pore pressure will definitely trigger fault. But this is not, this direction, which is close to east-west faults, they are not, that's why I put it misoriented, in fact, when it comes to reactivation potential. Well, just reactivating here, 70% of faults are favorably oriented. The pore pressure that we need to get those activated, in a sense, 7 megapascals or more will trigger slippage. Okay. With that, I'm going to conclude this talk and open for questions. Sorry for going over time.
Question?
I was going to say, Professor, is there legislation that if you are a fracking type company that you know how much you can do, where you should go, and where areas you are forbidden? Or can that be enforced in Kansas with our, lust for oil?
I think that there are guidelines, but they're not yet really refined to say map every fault. It is kind of undertaking that will cost money and data instead. But there are apparently just simple regulations they have introduced, only controlling the volumes of disposal water or disposal wastewater. It did produce some encouraging results. But when you need to go beyond that, in fact, and intervene from the point of really locating when, where to put a disposal, when, and what formation you inject. I think the bucket has received too much, and but when it is the deepest one, that's why it's favored.
Does Oklahoma have any similar regulations?
I'm not really sure about that, but for sure they have acted on what they have seen. I mean, they have seen seismicity in Caribbeans more than what we did. But they know they were injecting 500,000 gallons daily, and that's a lot of wastewater disposal.
Doesn't Coke, like if they're injecting toward northern Oklahoma, that would affect Kansas, wouldn't it? Or does it stay more local?
No, the epicenters will be on their side, but we'll feel the earthquakes, okay, because of it is close. But what we have seen in Sumner County and Harper County, in fact, the industry has a responsibility there, I would say. The alcohol industry.
So most of this is related to actually injections. So if they're not injecting, then, for example, if you go west of, on the other side of the Smoky Hills, you go into Russell County, those areas that have high rates of oil and so forth, but your graph, your map, didn't really show any activity out there. Does that mean that they're not injecting out there, their wells, to get the last part?
For sure they are injecting, but not at the same volumes and rates as in Harper and Sumner County.
Oh.
Yeah. Rates and volumes matter, and that has been proven actually by when they introduced the KCC regulations, it did show decline in the number of events.
Yeah. Okay.
I just wanted to comment that I think I came here with a big misperception, that you've kind of reoriented my understanding. I know so little about this, but when I heard about fracking as fracturing to get oil and to inject this stuff, I thought that the earthquakes were caused by breaking up rock structures. And what I learned here today is that it's this reactivation, which I find completely fascinating because that's a very different way of seeing it. So I wanted to say thanks for helping fix my assumptions.
Thank you for giving me credit for that. But I want to say that hydraulic fracturing would also produce seismicity, but not on such a scale, not like actually wastewater disposal. Because hydraulic fracturing, it does weaken the formation because it doesn't reduce fracturing. But these are small fractures. I mean, we're talking about the thickness of, say, 20, 25 foot rock formation. Okay. It's not like we're causing a slippage with an order of hundreds of meters or foot. You know. So it's completely different because hydraulic fracturing would introduce some level of seismicity, but not beyond 2 or 1.5 or even less. So they're not really as significant as such case.
But the wastewater is from the fracking process, right? What's this wastewater from?
Wastewater can be parts of it comes from fracking, another comes with when you produce crude oil. It's not 100% crude oil. Crude oil could be 40% of the volume and the rest is just brine. So injecting it back is good in a sense, but it should be regulated and not in one place. It should be distributed, so the effect would be less. Might maybe modeling and give more specific answers on that. But it is like, you know, I have seen the kind of funny video of bears. Bears, when they see that the ice is thin, when they spread their body, they don't walk on their feet because they want to distribute the weight. And so the ice wouldn't break on them. Likewise, in this case, well, spread the load, okay, not concentrate injectors in one county. So I don't know this. Of course, permitting should play a role there, and more analysis for really mapping the faults in the area. And well, a lot of work has been done, but there's still some work is ongoing. More answers, I think, in the next few years.
I have another question, if I may. Since in California, there are a lot of different faults, and that was clear on your map, are there very strict regulations about not injecting in along that area, or is it simply because they're not drilling?
Yeah, California, they're not the major producer of hydrocarbons. So I don't think they are suffering from this problem. But they do have their own level of high seismicity that is related to natural causes, basically.
So it would seem very risky if they were injecting fluid from anything, from oil wells or any other nuclear reactors or any other sources.
I am not aware of any major, say, waste disposal in California. Especially along this area, it will be really with kind of high risk undertaking. Because the San Andreas fault system is just not one fracture, it is a system of fractures. And you just want to stay away really from messing up with it because it's capable of producing major earthquakes.
Just give me a hand. Thank you very much, and I'm glad you could use the wrapping paper. So we will not have a lunch and learn in December, but we will have one in January, and I am not remembering right now. We talked about what it would be, but we will let you know ahead of time, and thanks again, Dr. Raef.
Thank you.
for